In this video we start a new chapter on normal subgroups and factor groups. So we begin here with a chapter on normal subgroups. So we begin with a quick definition of normal subgroup. A subgroup H of a group G is called a normal subgroup of G if AH equals HA for all A in G. Usually we write it this way: H normal subgroup of G. So this is the usual notation. Do not forget that for subgroup this is the usual notation. H is a subgroup of G. H is a subgroup of G. For normal subgroup we write H, a sort of a triangle, subgroup of G. So basically the left cosets are equal to the right cosets of a subgroup H. So H is a subgroup of G. Okay, H is a subgroup of G, and if the left cosets are equal to the right cosets, then we say H is a normal subgroup of G. So we immediately start with a theorem that will help us to check if a certain subgroup of G, if it is normal or not. I'm going to call this the normal subgroup test. A subgroup H of G is normal in G if and only if inverse image, so X is an element in G, okay, so inverse image, the left product, the inverse image times the subgroup times X is a subset of H. If this happens, then we say H is a normal subgroup of G. I want to call your attention immediately to a very important point. Usually many students make the mistake of thinking that H is normal in G means AH equals HA for all A in G, and this is not true. Okay, that's not what being normal means. Okay, because A should be in G and H should be in H, right? But this is not what normality is. Normality is this product, okay, the left product and the right product with a certain subgroup of G. Okay, first example. The center of a group is always a normal subgroup of G. Very easy to prove this. Okay, some other examples are, so the center of a group is always normal in G. The alternating group AN of, this is the even permutations, is always a normal subgroup of the symmetric group of the same order, of course. Third example, the subgroup of rotations dn is always a normal subgroup of dn too. And another example is the special linear group. Some people write this, I keep saying this over and over, I don't know why. Write this way, but I prefer to write this way. So the special linear group of matrices dimension 2 by 2 with entries in the reals. So this means matrices with determinant equal 1. This is not only a subgroup of the general linear group of matrices 2 by 2 with entries in R, with non-zero determinant. The determinant here equals 1. The determinant of these matrices equal 1, and the determinant of the matrices in the general linear group are not 0. Okay, so the special linear group of matrices of dimension 2 by 2 with entries in R is a normal subgroup of the general linear group of the matrices of dimension 2 by 2 with entries in R. So we move now into factor groups, and this will be a new chapter. We just saw what normal subgroups are. For instance, H being a normal subgroup of G. Why is this important? Well, if you have H a normal subgroup of G, then the set of left or right cosets of H in G is itself a group. And this factor group of G by H, this is called the factor group of G by H. I will introduce that in a second. Okay, this is also called the quotient group. The quotient group of G by H. Okay, I think I will end up calling it factor group. Okay, so this will be the set of left or right cosets of H in G. Okay, so we introduced this very important theorem about factor groups. Let G be a group and H a normal subgroup of G. So H is a normal subgroup of G. The set quotient group of G by H, or factor group of G by H, is the set where element A in the set G, A in G, A times the subgroup such that A is in G, is a group under this operation. So we have this set, okay, left, and of course then right. We will see that in a sec. So this is the set, and the operation is this one: AH, BH, B subgroup equals AB, So this set under this operation is a group. I read somewhere that this notation for factor groups is due to Jordan. I have to check if this is true, and I also have to check if Hölder in 1889 is the author of this theorem. So we do the proof, and first we have to show that this operation is well defined. I mean, if the factor group times, right, the factor group into the factor group, if this is actually a function. So is the factor group of G by H operation with another element of the factor group of G by H mapping into the factor group of G by H, is it well defined? Do not forget we will be using the fact that H is a subgroup of G. Okay. No, sorry. We are using more than that, right? We are using the fact, so the theorem says let G be a group and H a normal subgroup of G. Okay, so we are going to prove that the set under this operation is a group. Okay, so by hypothesis H is a subgroup of G. Okay, I want to remind you also some properties of cosets. This is in the previous video, but I don't know the number of the video now, not offhand. So the properties of cosets are 1. A is always in the left coset. Of course, A is always in the right coset too. 2. Oh, this is very important because we are going to use this one. The left coset of H times A equals H if and only if A is in H. So if A is here in H, the left coset will be H itself. Okay, 3. A times H equals B times H, or AH, the intersection of AH. If these two are equal, it's the same as saying that AH intersection BH, the intersection is empty. Okay? AH equals BH if and only if the inverse times B is in H. This sounds a bit like the subgroup test, right? Okay, the order A times the subgroup H equals the order of B times H. AH equals HA if and only if the subgroup equals the product of inverse of A, H, A. 7. AH is a subgroup of G if and only if A is in H. So back to the proof. We have to prove that if I pick two elements in the factor group and I map it in the factor group, that this operation is well defined and that this is a function. Okay, so in order to prove this, we are going to assume that AH equals A prime H. And we also assume that BH equals B prime H. Okay? So, okay. Then we can say that I'm going to write it here, that A prime equals A times an element here, H1, okay? And we can say that B prime, you can check this is very simple, times BH, but I'm going to call it 2, okay? Okay. For some H1 in H2 in H, right? So if this is true, A prime B prime H equals, so A prime is this, right? So equals A H1 B H2 H, right? Okay, so this means okay, this step is only due to this notation, okay? A prime is A times H1, right? So A prime is this and B prime is this, so B prime is this, okay? Now this step we have to go back to, I'm going to use this second property, AH equals H if and only if A is an element of the subgroup. Okay, so let me see if I write this well. So I'm going to write A H1, that's what it is here, and B H2, but here I can write BH, right, since H2 is in H. Okay, and do not forget this is a normal subgroup, so I can also write normal, this step is because it's normal, AH1 HB. Okay, and now for the same property I can write A, here I can write A H B using the same property. Okay, but this is a normal subgroup, so this will be A B H. Okay, so we use that second property. Okay, we use that second property, and we also use the fact that H is a normal subgroup of G. Okay, and now to check that this is a group, the rest of this is really easy, because identity H equals H, so this is the identity, right? And A inverse times H will be the inverse of AH, right? Really easy. And if you have AH if you have AH BH times CH, so this is normal, right? So we can do AB like this and H CH, right? But here you can do AB. So H times H is H, so we can write CH. And now we can write, hey, H, these two times BCH. And now AH, BH, CH. And this concludes the proof. So we can say that the factor group under that operation is a group. So if G is a group and H a normal subgroup of G, this set, so left coset of H, is a group under the operation AH-BH equals ABH, as we just proved.